Morning everybody. This video that I'm making today is to introduce the unit circle to you if you haven't already seen it, and I'm going to use the unit circle to talk about a different unit of measuring angles, which is called radians, and also to use the unit circle to introduce sine, cosine and tangent, and then finally we'll have a look at where the trigonometric ratios sine, cos and tan come from for right angle triangles. And they all stem from this basic circle. It's called the unit circle because it has a radius of 1 unit, and because it is just about physical lengths in a circle, this is actually pretty much a measurement topic, or it links to geometry as well. So measurement and geometry, put those two together and we get trigonometry. Alright, so let's start with the unit circle. Really simply, we know that a circle has angles which we have looked at in the past, which might be 45 degrees, or we might have 90 degrees, and if I do half a circle I've got 180 degrees, if I do 3/4, 270 degrees, and then finally a full loop of a circle is 360 degrees. So we've seen degrees before lots of times. Okay, we understand degrees as a measurement of an angle. So what the radians is about is it's a way of calculating angles in a slightly different way. And radians is about measuring the distance from the positive x-axis around the circumference of the circle to a point. So if I want to work out this angle in radians, I would be looking at is what is the length of this arc. And I'll actually work that out soon, but not just right away. So the length of this arc here, that would be the measurement of this angle in radians. So we would have the angle of this in radians. Now for radians we can put a little r instead of the degrees sign. That's used in some textbooks, or you'll also see it's with a little c. Now the little c makes sense because it's the measure of the circumference of the circle. Okay, so let's get rid of all of that for a second and go back to the beginning on our unit circle. So let's start with looking at what is the circumference of the unit circle to start with. Now, if we know radians is the measure of the circumference of the circle from the start all the way to the finish, then I can start with my basic measurement formula that circumference is equal to 2 pi r, and in this particular case it is the 1 unit circle, so it's 2 pi times 1, and we don't need to write the times 1, so we just get 2 pi. So that gives us that 360 degrees, one full circle, one full revolution is equal to 2 pi radians. Press the wrong button there. 2 pi radians with a little c. So one full revolution is 2 pi. We can say it's 2 pi, or we could say it's 360 degrees. They're the same thing. So really logically then, if I want to do half of a circle instead of a full circle, let's change the colour, let's use green. If I want half of a circle, then I can just halve both those parts. And we've seen this in degrees, so half of a circle is 180 degrees. It's half of a revolution. Now if we've halved the 360, we can also halve the 2 pi, which gives half of a circle is equal to pi radians. So this angle over here in radians is pi. In degrees, it's 180. Alright, let's keep going about this in the same manner. Let's now look at a quarter of a circle. Well, if we went quarter of the way around, logically a quarter of the way around, we have seen is 90 degrees. So we know that as degrees. That's a quarter of a revolution. So if we do 2 pi broken up into quarters, that's the same as having 1 pi divided by 2. And we get a quarter of a circle is known as pi on 2 in radians. So we're starting to create all of these angles in terms of pi. And so that's why we will see our radians in terms of pi a lot of the time. But just for the record, they don't have to be in terms of pi. So if I take pi divided by 2, that's approximately 3.14 divided by 2, which is approximately 1.67. Okay, we've rounded off to 2 decimal places here, so what we prefer to do is to keep the exact value and keep the pi's in there. So we're using the pi's so that we maintain our exact values with irrational numbers. Okay, so let's go a little bit further now. Let's have a look at, I should have kept that pi on 2 there, I'll just keep the pi on 2. I can continue and sort of like start breaking up all of these angles. I can have that 45 degrees. Well, that's half of 90 degrees, so if I half a half, that would give me pi on 4. So 45 degrees is pi on 4. And that's actually the angle that I showed you right at the beginning when I went to here. Because I've split that 90 degrees in half, so that's 45 degrees, or it is pi on 4 radians. And then I can keep going like this, and I can create a whole heap of other angles. So if I halve the 45 degrees, I'd have 22.5. 22.5 is pi on 8. But the really common angles that you will see, I'll get rid of the 45, and I just, undo that. Just need to try and create a little bit of space in my circle here. The common angles I will see will be 45, 30, and 60 degrees. So they are roughly about there. 180 degrees, which we've seen. So 45 is pi on 4. 30 degrees is pi on 6. And 60 degrees is pi on 3. So they're our really common angles that we use in radians because they have nice little neat fractions. But let's say I wanted to work out what 1 degree was. So if I want 1 degree way down here somewhere, I can start with, very simply, 360 degrees is equal to 2 pi radians. If I divide both sides by 360, then I end up with 1 degree is equal to pi divided by 180 radians. And I can use this to convert any angle into radians. So any angle in degrees into radians. And the way I do that is if I multiply both sides by some angle, n, then, for example, if I wanted to have 47 degrees, 47 degrees would be the same as 1 times 47. And to convert that to radians, I would take the pi on 80 and times it by 47, which gives me 47 pi over 180 radians. So there's 47 degrees written in radians. Alright, so the last thing I wanted to say about radians is we can keep going around the unit circle. So if I wanted to go all the way around to, say, some point here. So this splits the third quadrant into half. So I know that that part is 45 degrees. And I know that this top part is 180 degrees. So I know that this angle in degrees is 225 degrees. Well, what is it in radians? So let's have a look very simply in radians, and if I use yellow here, this line here is my first 45 degrees. If I added another 45 degrees to that, it would take me to pi on 2. If I added another 45 degrees, it would take me over here to 135 degrees. Another 45 degrees takes me to 180. And then finally, I get my fifth lot of 45 degrees here. So what I can do, I can count by pi on 4s here. So this first part is 1 pi on 4, 2 pi on 4, 3 pi on 4, 4 pi on 4, and finally 5 pi on 4. So the first one was 1 pi on 4, then 2 pi on 4s, 3 pi on 4s, 4 pi on 4, and finally 5 pi on 4. So I'm actually just counting on, but instead of counting by 45 degrees, I'm counting by pi on 4 radians. Okay, so that's the basis for where radians come from. And this formula down the bottom here, I'll just highlight this formula that I wrote earlier. That formula there is going to be pretty important to help you convert from degrees to radians. And you'll need to do that in one of your exercises. And there's more examples in your book. Okay, let's have another look at the next part. So the next part is about where do sine, cosine and tan come from in the unit circle. So I'll just scroll up here. So the first thing is we're starting to look at angles, and those angles can be anything. So here's some angle, not quite 45 degrees this time, not quite 30 degrees this time. We don't even know what that angle is. So I'm just going to call it theta. So theta to represent an unknown angle. Now, I don't know what that angle is, but I do know that the length of this line, the length of the hypotenuse, is equal to 1 because it's the radius of the unit circle. So I know that the radius is 1, I know that the length is 1, but that doesn't really help me work out the angle. What sine and cosine are about is they're breaking up these angles or these components of the unit circle into its vertical and horizontal components. Okay, so sine and cosine is a way of breaking up that length, that line there, into its vertical and horizontal components. So let's give them a different colour each. Let's use the vertical part, call it green. Really simply, we've got the vertical component. And then different colour, let's use orange just because I found orange first. And then that's my horizontal component. Okay, now the thing with these vertical and horizontal components is when I change the angle, let's say for example my line was up here instead, then the vertical part will get longer. The horizontal part will get shorter. Okay, so the vertical and the horizontal parts are going to change based on the angle. So if the vertical and the horizontal parts aren't constant, that means they have a variable. That means they are a function of the angle, or they function in relation to the angle. So what we do, or what somebody did, is they decided, well, let's write the vertical component as a function of the angle. And for whatever reason, they decided to call the vertical part sine. And they said it functions based on the angle. And then the horizontal part, they decided to call cosine. And it functions based on the angle. So we've set up these two functions, sine and cosine, which are dependent on the angle. but cosine's the horizontal distance and sine's the vertical distance. Okay, so let's actually undo some of that writing. We'll go back here a bit. And let's have a look at, well, how do sine and cosine actually work? What do they actually do? So, all due to the unit circle here, let's get rid of that angle. Let's say I had the angle of, we can use radians or we can use degrees. Let's say, oops, sorry, just zoomed in too much by accident there. Let's say I had 60 degrees. So 60 degrees, I need to break this up into 3 equal parts. 60 degrees is about there. I have estimated this angle of 60 degrees, or if you like, pi over 3 radians. Since we've started talking about radians, we've got 60 degrees, we've got pi on 3, that is our line. What I can do is I can break this angle up into its vertical and horizontal components. So let's have a look at that vertical component. Here's the vertical component. We can see it there as this nice green line. And my vertical component is known as sine. So that green line there would be what we call sine of 60, or sine of pi on 3. Now notice when I write it this way, I'm not saying sin, I'm saying sine, because the SIN is an abbreviation of SINE. Okay, so sine of 60 and sine of pi on 3 are equal. And the other thing is, because they are a vertical distance, I can go over to my y-axis here and I can estimate what the physical distance is here. So I can come up with an approximate value. So if it's the vertical distance, and I know that from the origin all the way up to the unit circle is 1, then halfway would be 0.5. Okay, if I use the grid that I've got in the background, here's 0.2, 0.4, 0.6, that's not a 6, but I'll fix that in one moment, 0.6, 0.8. So we could estimate that this isn't quite 0.9, but it's bigger than 0.8. I could estimate from my diagram, where I've guessed where 60 degrees is, I could estimate that sine of 60 degrees, or sine of pi on 3, is 0.87. And I'm just going to type that into my calculator and see what I get. Sine of 60 degrees is 0.866. So I didn't set this up, that's my hand-drawn diagram and my estimation of where 60 degrees is, and I am within 1/100th accuracy. Okay, so really, really close just by using a physical measurement. So then let's go to the cosine value. Let's see if I can get it as close this time. So the cosine value is the horizontal distance. And again, this is 0.2. This is 0.4. So that on my diagram is just a smidge bigger than 0.5. So I could say that cosine of 60 degrees is the same as cosine of pi on 3, and I'm estimating from my diagram at 0.52. Now the actual value for cosine of 60 is 0.5. So you can see again, using the physical length of my hand-drawn diagram, I'm able to estimate those values really, really closely, because they're just lengths. Sine and cosine are just lengths. Alright, let's rub out some of this extra stuff here and try and get back to a basic diagram so I'm not too confusing. I want my red line though. Let's just get rid of these green bits. Still can't get rid of it. I'm going to leave that dot there. Okay. So what about tan? What's tangent? Well, a tangent line is a line that represents a curve at a point. So if I drew one single straight line to represent the unit circle where it hits the x-axis, that line would look like this. Okay, let's just make that a little bit thicker so it's easier to see. That's maybe a little bit too thick. Let's change that back a bit. That's pretty good. Okay, so this line represents the curve at the point where x equals 1, or at the point where it hits the x-axis. This is known as the tangent line. Now there's other ways of describing what the tangent line is, but I'm going to stick with this one. I like it for simplicity. So if I kept my line at 60 degrees going all the way up until it hits the tangent line, then the length here is equal to tan of 60 degrees. And again, I can use the y-axis to help me estimate there. If that's 1, then tan of 60 degrees is going to be roughly, I'm going to say that was 1, so that's 1.2. 1.2, 1.4, 1.6. So I'm going to say tan of 60 degrees is equal to the same as tan of pi on 3, and that's approximately 1.6. So if I type that one into my calculator, tan of 60 degrees, it's 1.73. So not quite as accurate that time, and probably because you can see that my line's getting a little bit curved there. But we're still able to estimate the value of tan using this tangent line. So the next part of that, let's go right back again, and we'll get rid of some of those extra parts. So I've got a less confusing diagram. I'm going to get rid of 60 degrees this time. I'm going to say, well, let's have a look at a different angle. What if I had, let's say, I don't know, 180, let's go 60 more. So let's say 240 degrees. 240 degrees is roughly down here. So there's my 240 degrees. And that we know is 240 degrees, which means that part there has to be 60 degrees. So if that's 60 degrees, we're working in, let's have a look at the radians very quickly. So 240 degrees, this part here is 60. So that means this length here is the same as what we're working with before, pi on 3. And I know that 180 degrees is pi. So this point here, if I wanted to go in radians, it's pi plus pi on 3 radians. Or 3 pi on 3 plus pi on 3 radians. We've got to use our fraction skills here, and that gives me 4 pi on 3 radians. So we've got an angle of 4 pi on 3. If I look at, let's go back to what we were talking about before, the vertical distance at that point. The vertical distance would be roughly here. And that vertical distance is very similar to what we had before. Sine of, not 60 this time, sine of 240 degrees, or sine of 4 pi on 3 radians. That will be the same as before, except it's not positive this time, it's negative. Oh, that's not a negative sign. What am I doing? So it would have to be a negative 0.87. And my cosine value is this horizontal distance here. And same thing as before, that horizontal distance is going backwards. So cosine of 240 is the same as cosine of 4 pi on 3. And in this case, it's not equal to 0.5, it's equal to negative 0.5, because I'm on the negative x-axis at that point. So we can find angles in the unit circle, all of those angles from 0 to 360 or from 0 to 2 pi radians and beyond, and they will always be a number that comes from the horizontal or vertical length on the unit circle. Alright, this video is turning out to be a long video, so I'm going to go very quickly into the last part here. What we've just been seeing is a whole heap of triangles. And not any triangles, but when we break those triangles up into their horizontal and vertical parts, we create a whole heap of right angle triangles. And in my unit circle, the side lengths of these triangles are given like that. If I have any triangle at all outside of the unit circle, we can label the sides as the opposite, the adjacent, and the hypotenuse, like this. Now, because these two triangles share the same angle theta, and they share a right angle, that means the third angle up here would also have to be equal. And when all three angles are equal, they're called similar triangles. So in this case, we've got two similar triangles. One's bigger than the other, but because they're similar, the side lengths have to have the same ratio. So what that means is if I took the side length of sine and I divided it by the hypotenuse, it would have to be the same as this side length divided by the hypotenuse. So what that gives me is the ratio of sine theta divided by the hypotenuse, which is 1 in the unit circle, has to be equal to the opposite side divided by the hypotenuse in any other triangle that has the same angles. And hence, we end up with the trigonometric ratio for right angle triangles that sine theta is equal to the opposite divided by the hypotenuse. And if we repeat this for cos theta, so again, if I take cos theta divided by 1, that has to be the same as the adjacent side divided by the hypotenuse. They have to have the same ratio. And that gives me that cos theta has to be equal to the, or cos theta divided by 1 has to be equal to the adjacent and again we don't need to divide by 1, so we get the rule for a right angle triangle is cos theta equals the adjacent over hypotenuse. So as long as they have the same angles, these ratios have to be the same. And the final one, which is tan, I'll talk about at a later date, because tan involves, actually no, I'll do a very quick version of tan here, but tan can also be considered in a few different ways. So there's my tangent line. If I take that length there as tan theta, we've created a different right angle triangle here. But I do have that cos is equal to 1 in this case. So if I take tan theta divided by 1, that would be the same as the opposite divided by the adjacent. And I get that, I'll rub that out, tan theta divided by 1 has to be the same as the opposite divided by the adjacent. Okay, so there's a lot in that video and it's become a very long video, so I'm going to stop that there. And that is our introduction to the unit circle.